this module, you will learn about hydrides. You have learned that dihydrogen combines with almost all the elements except noble gases under suitable conditions to form binary compounds called hydrides. These can be represented as EHX or EMHN, where E is the symbol for an element. For example, MgH2 or B2H6. There are three types of hydrides depending on the behavior and the nature of the bond formed between the hydrogen atom and the element forming the compound. The types of hydrides are ionic or salt-like hydrides, covalent or molecular hydrides, and metallic or non-stoichiometric hydrides. Let us look at each type in detail. Ionic or salt-like hydrides are binary compounds of hydrogen with S-block elements that are highly electropositive in nature. However, compounds formed with lithium, beryllium, and magnesium exhibit higher covalent character. Ionic hydrides like sodium hydride and calcium hydride are formed by the transfer of electrons from the metal atom to hydrogen atom. This is also why they are called salt-like hydrides. Ionic hydrides are crystalline in solid state. They have high melting and boiling points. Their density is higher than that of the metals from which they are formed. In the molten state, they conduct electricity and, on electrolysis, liberate hydrogen gas at the anode, confirming the presence of negative ions of hydrogen in them. Let's study this using calcium hydride as an example. On passing current through molten calcium hydride, the compound dissociates into calcium 2+ ion and hydride ion. At the anode, each of the two hydride ions combine to liberate dihydrogen gas and 2 electrons. This is an oxidation reaction. At the cathode, each calcium 2+ ion accepts 2 electrons to give calcium. This is a reduction reaction. Ionic hydrides react vigorously with water to liberate dihydrogen gas. For example, sodium hydride reacts with water to give sodium hydroxide and hydrogen gas. Ionic hydrides decompose into highly inflammable dihydrogen and undergo combustion when strongly heated in air. For example, calcium hydride, when heated at 675 to 775 Kelvin, decomposes into calcium and dihydrogen. Unlike other ionic hydrides, lithium hydride is unreactive at moderate temperature with oxygen and chlorine gas, and is used in the synthesis of other useful hydrides such as lithium aluminium hydride and lithium boron hydride. The reaction that takes place is lithium hydride reacts with aluminium chloride to give lithium aluminium hydride and lithium chloride. Lithium aluminium hydride is a powerful reducing agent and used extensively in organic chemistry. Lithium hydride also reacts with boron hydride to give lithium boron hydride. The second type of hydrides are covalent or molecular hydrides. Covalent or molecular hydrides are binary compounds of hydrogen with more electronegative elements, such as p-block elements. They are bonded by covalent bonds. For example, CH4, NH3, H2O, and HF. Covalent hydrides are further classified into three types, depending on the number of electrons and bonds present in their Lewis structures. The three different types are electron-deficient hydrides, electron-precise hydrides, and electron-rich hydrides. As the name suggests, electron-deficient hydrides do not have the required number of electrons to write their conventional Lewis structure. In other words, they do not have complete octets. The hydrides of group 13 form electron-deficient compounds. For example, in borane BH3, boron has 3 electrons in its outermost shell and forms 3 covalent bonds with 3 hydrogen atoms, resulting in an incomplete octet with only 6 electrons. Another example is aluminium hydride or alane, AlH3. Due to their incomplete octets, these hydrides generally exist in polymeric form. For example, BH3 exists as diborane B2H6. They act as Lewis acids, that is, electron acceptors, as they are electron deficient. Electron-precise hydrides have the required number of electrons to write their Lewis structure. In other words, they have complete octet and are formed by the elements of group 14. For example, in methane CH4 and silane SiH4, both carbon and silicon have 4 electrons in their outermost shells and form 4 covalent bonds with 4 hydrogen atoms to complete their octet. Electron-rich hydrides have excess electrons, which are present as lone pairs. The elements of group 15, 16, and 17 form such hydrides. For example, NH3 has 1 lone pair on nitrogen. H2O has 2 lone pairs on oxygen. And HCl has 3 lone pairs of electrons on chlorine. Due to the presence of excess lone pairs, these hydrides behave as Lewis bases, which are electron donors. These hydrides also form hydrogen bonds between molecules due to the high electronegativity of nitrogen and oxygen. Electron-rich hydrides are poor conductors of electricity and are soluble in organic solvents. The third type of hydrides are metallic hydrides. They are binary compounds of hydrogen with D and F block elements. However, except for chromium from group 6, the metals of group 6, 7, 8 and 9 do not form hydrides. The inability of these metals to form hydrides is called the hydride gap of D block. Metallic hydrides are deficient in hydrogen and are almost always non-stoichiometric. For example, LaH2.87, YbH2.55 and TiH1.521.8. The composition of these hydrides does not correspond to simple whole number ratio and also varies with change in temperature and pressure. And hence, these hydrides are also called non-stoichiometric hydrides. Earlier, it was thought that hydrogen, being very small in size, occupied interstices in the metal lattice in these hydrides, and hence they were named interstitial hydrides. However, recent studies have shown that except for the hydrides of nickel, palladium, cerium, and actinium, the other hydrides of this type have lattices different from the parent metal. The property of absorption of hydrogen on transition metals is widely used in catalytic reduction and hydrogenation reaction in the preparation of a large number of compounds. Metals like palladium and platinum can accommodate a very large volume of hydrogen and can be used as media for its storage. Metallic hydrides are good conductors of heat and electricity and are harder than the parent metal. You have now reached the end of this module. In this module, you learned that there are three types of hydrides: ionic or salt-like hydrides, covalent or molecular hydrides, and metallic or non-stoichiometric hydrides. Ionic or salt-like hydrides are binary compounds of hydrogen with s-block elements, which are highly electropositive in nature. Covalent or molecular hydrides are binary compounds of hydrogen with more electronegative elements, such as p-block elements. Covalent hydrides are further divided into electron-deficient hydrides, electron-precise hydrides, and electron-rich hydrides. Metallic hydrides are binary compounds of hydrogen with d and f block elements. Except for chromium from group 6, the metals of group 6, 7, 8, and 9 do not form hydrides. The inability of these metals to form hydrides is called the hydride gap of d block.